Okay, so the purpose of this question, guys, from yesterday was to illustrate the importance of having a reference point when you're dealing with vector quantities. Okay? When we had the Inukshuk question yesterday, the Inukshuk was the reference point. Everything was measured from there. Okay? In this question, we have to draw a seating plan, okay, from one of the people given to us. All right? So if we're going to do this, okay, we're going to start out with the first thing they tell us, which is that Chad is 2 meters to the left of Dolores. Do I know where Dolores is? I don't. But I know Chad is 2 meters to the left of her. So I'm just going to do this. I'm going to put Dolores right here, but not with the big marker. Okay, I'm going to put Dolores right there, and then I'm going to put Chad 2 meters to her left. Okay, Ed is 4.5 meters to the right of Chad. Okay, Greg is 7.5 meters left of Chad. Okay, so there's 4.5. I need another 3. Okay, so that's Greg. Okay, and Hannah is 1 meter right of Ed. Oh, sorry, I put Ed in the wrong place. Sorry, guys. Let me back that up. I put Ed left when he should have been right. I promise I know my left from right. Okay, Ed is 4.5 meters right of Chad, which makes him 2.5 meters right of Dolores. Okay, Greg is 7.5 meters left of Chad. Okay, and Hannah is 1 meter right of Ed. Okay, who did I need to place before I could put anybody else down? Dolores. Dolores was my reference point. Everyone else was measured from her or measured from someone I placed after her. Okay, so Dolores actually was my reference point because everything came from her original referral. She's only mentioned once in the whole question. Okay, Chad's mentioned like 3 times, but I couldn't put Chad somewhere until I put Dolores somewhere. Okay, so that sort of makes sense? Okay, so any vector question you have is going to have a reference point, usually your initial position. Okay, but sometimes your initial position is placed reference to something else, like the Inukshuk question we had yesterday. All right, so second part of this question, what's the displacement of a teacher who walks from Greg to Hannah? Okay, well, 7.5, 9.5, 12, 13 meters to the right. Okay, would be my final answer for the last part there. Okay, questions on that one? Okay. Now, I want you to try question number 6 here. Okay, this diagram goes with question number 6. My hint to you is read it carefully. It's very easy to make kind of a knee-jerk reaction to this question if you don't read it carefully. Okay. All right, so the ball, okay, that these people are hitting back and forth, okay, we know that they're standing 3 meters apart. Okay, the child on the right tosses the ball to the child on the left and then moves 5 meters to the right to catch the ball again. Determine the total distance and displacement that the ball travels from its initial position. Okay, so displacement is just how far it changes its position. Where did it start? With the purple or the green? Purple. Okay, so this is my initial position then. Okay, and my final position is apparently over here. Okay, because the person moved 5 meters to the right to catch the ball. So what's the displacement of the ball?
5 meters right.
5 meters right. Okay, final position minus initial position is 5 meters right. Okay, now what's the total distance traveled by the ball?
11 meters.
11 meters. Okay, if you put 8, that's the knee-jerk answer. Okay, because you look at the 2 numbers that are on there, 5 and 3 is 8. Okay, except it went over that 3 meter section twice. Okay, the person tossed it this way and then it went that way. So the purpose of this question is to illustrate how we draw vectors, okay, or vector addition type questions so that we include all the parts, okay? If the ball started here, the first part of this trip is this 3 meters, okay? After that, the ball goes all the way over here. Okay, everyone all right with that? We always draw our vectors in this way. We call it tail to head, right? I put the tail of the second vector, that's the blue line, onto the head of the first, or I drew it from there, like I was telling a story. First I went 3 meters to the left, and then I went 5 meters to, or I went 8 meters to the right. Okay, everybody all right with that? Okay, so just to illustrate that, because that's going to be something big when we get into real vectors involving trigonometry and all that, okay, drawing all these angled lines and arrows and stuff that we have to keep track of. Okay, everybody all right with that? Okay. All right, that one we will skip. Okay, manipulation here, guys. Okay, just quick algebra lesson. What are the 3 rules of algebra? If I want to move something, I do the opposite. Okay, so if I'm multiplying, I would divide, and if I'm adding, I would subtract. Okay, second rule, the golden rule of algebra. What I do to one side, I must do to the other. Okay, third rule of algebra, the one that's usually forgotten. I move what's not attached to what I'm looking for first. Okay, in V equals D over T, rule number 3 doesn't apply. Okay, but in a question like, or in a formula like this one, it would. Let's say I want to solve for M. What would I move first?
B.
B. B is not attached to M. Therefore, I would move it first. Okay, I would subtract B over to the other side. And then what would I do? Divide by X, because I'm looking for M. Okay, and what I do to one side, I do to the other. Okay, I follow the rules of algebra. Okay, if you can remember those 3 rules and follow them, you can get through this course, no problem. Okay, and I say that from experience. Those 3 rules got me through university physics. Okay, just being able to remember those 3 rules of algebra. Okay, once you get into the calculus-based stuff, all bets are off. Okay, but as long as you're doing the linear stuff, those 3 rules will get you through. All right, so if I wanted to manipulate this formula to solve for D, what would I do? I want D by itself.
Multiply by T.
Right, multiply both sides by T. Whoa, I want both parts of the T to come. Okay, T times V equals D. All right, what if I wanted to solve for T?
Multiply by D.
What's that?
Multiply by D.
If I multiply by D, then I'm putting another D over here, right? What's D times D?
Oh, wait,
D squared, right? Okay, so we can't do it that way, but that's all right. Okay, here's something to think about. When I solve for something, do I want it on the top or the bottom?
Top.
Top. Otherwise, I'm solving for 1 over that number, which is not the same as that number. That's like saying 2 is the same as 1/2. Okay, they're definitely not the same. So do I need to move T first? Because right now it's on the bottom. Okay, so I do what I did before. I multiply both sides by T. Now T is on the top. What do I do with V? Divide it over the other side. Okay, you can always double check your algebra by doing a unit analysis. When I put D over V, I've got meters divided by meters per second. Will that leave me with seconds? Are those the units I should get for time? They are. Okay, so you can always double check by doing a unit analysis to see if you've done it right. Okay? All right. There's the question we missed here. Where was it? Must have it on another one. Okay, here's what I would like you to do. I'm going to put some questions up on the board. They're actually from your worksheet. Okay, and I want to just see how you do with these. All right, that one's too easy. So is that one. Okay, I want you to try this one. Okay, from Science 10, these were our 2-part finding average velocity type questions. Okay, so when you're writing out your givens, you've got a part 1 and a part 2 and then a total. Okay, so the hint I will give you here is this. When we write this formula, what it really means is this. Average velocity is total displacement over total time. Okay, that's going to come into play for this question. I'll give you a few minutes on this one. See what you remember. Whoop. I want the eraser. Read my mind. Come on. Average speed is total distance over total time. So this question wants me to calculate the average speed. If I'm going to get average speed, I need two things. The total distance traveled by the object and the total time it takes to do that. Okay? Those are the two things I need. So, as I was saying, to start this off, you want to write out your givens, okay, according to the parts of the question. In part 1, the bus travels 11 kilometers at 21 meters per second. Right away, I've got a problem. One of my things is in kilometers, the other's in meters. What do I need to do? Can I divide? Yeah, they got to be the same unit. Okay, otherwise it's apples and oranges. All right. So the first thing I need to do is convert the 11 kilometers into meters. How many meters in a kilometer? 1,000. So this is 11,000 meters. Okay, it's the first thing I got to do. There's a little metric trick here. Okay, 11,000 meters at 21 meters per second. Okay, that's what I know. So I've got part of the total distance, but I don't know how long part 1 takes. Can I figure it out? Okay, so I just have to manipulate V equals D over T for T, which we just looked at a minute ago. I just basically cross multiply V and T. All right, so T is going to equal 11,000 meters, okay, divided by 21 meters per second. So that is going to take 523.8 seconds. I'm going to keep all those decimals, but I'm not going to write them all. Okay, seconds. And then for part 2, okay, I know that they travel 1 kilometer, which is 1,000 meters, at 4.2 meters per second. Okay, so once again, I've got the distance, but I don't have the time. Do I do the same thing? Okay, do the same thing to get time here. So time is going to equal D divided by V. That's going to be 1,000 divided by 4.2. Whoop, not times 1,000 divided by. Okay, 238.09. Okay. Do I have everything I need now to get the total distance and the total time? Okay, so what do I do with the two distances? Add them together. Okay, my total distance is going to be 12,000 meters. Okay, we're dealing with distance, so direction doesn't matter, plus we weren't given direction anyway. Okay, and I've got to take the time and add those together. That one we're not going to do in our head. Okay. So we'll take our answer from there and that number there. Okay, and we have a total time of 761.9. Okay, can I get the average speed now? Okay, total distance over total time. So we take our 12,000, we divide it by 761.9. Okay, but with all of our decimals. Whoops, did that backwards. Okay, so the average speed ends up being 16 meters per second because we only have 2 significant digits in that question. Okay? Everybody all right with how that one works? Initially, that question looks a lot harder than that, doesn't it? Okay? So, anytime we're finding average speed or average velocity, this is what we have to do. Okay? We've got to find for speed, total distance and total time. For velocity, total displacement and total time. Okay? The only thing that differs for displacement is direction matters. So if you've got one part where it goes north and one part where it goes south, you've got to make one of those negative and take that into account. Okay? Everybody all right with that so far? Okay? We did do questions like that in Science 9, or Science 10, sorry, but that was quite a while ago. All right, let's see. Got another one here, but that's vector. Maybe we're not quite ready for that one. Let's try this one here. It's very similar to the last one you did. So basically the same as the last question, except this time it's a person jumping out of a perfectly good aircraft. Okay, so we've got person falling first 625 meters in 15 seconds. All right, so part 1, right, we've got a displacement this time because they did indicate direction. You generally fall down. Generally. Okay, and then the time is 15 seconds. And then in part 2, they open the parachute, that's good, okay, and they fall 356 meters, and that happens in 142 seconds, so they're obviously going a lot slower, okay, while the parachute is open. They want the average velocity, magnitude, and direction for the entire fall, so that means I need the totals. I need the total displacement. What do we do with those two numbers to get that?
Add them.
Just add them. They're in the same direction. They're both down, so I can just add them like they're positive. All right, so I think that comes out to 981, yeah? Am I right? Yeah, I shouldn't do it on that because I'm only right half the time. Okay, and then I'm pretty sure this one's 157 then. Okay. All right, so I've got my total displacement and my total time. This one's easier than the last one, right? Because we didn't have to do any intermediate calculating on that one. So we take our total displacement, divided by our total time, 981, divided by 157 seconds, gives us 6.2. We only have 2 significant digits. Oh no, we have 3 significant digits in this question. 3, 3, 3, and 3. Okay, so we should have 3 sig digs in that answer, making that 6.25 meters per second. What am I missing when I say that? Down. Yeah, exactly. I need to have a vector on that. They did ask, okay, for the direction for the velocity. Okay, is that ringing a bell? Okay. The graphing ones. Where's the one I want? I'm just going to make one up then. All right, copy this one down and give it a try. I think we're on example number 4 here at this point. Okay. Okay, that would be about as tricky as they would get. Okay, I'll give you a few minutes on that one. So same as the other ones, we've got a question here that has two different parts. The ant is going two different directions at two different velocities. Okay, so we're gonna go with part one. Okay, and in part one, we know that the velocity of the ant is 0.25 meters per second north. Okay, and we know that the time is 32.5 seconds. Okay, in part two, we know the velocity of the ant is 0.135 meters per second south, and we know that the displacement is 1.75 meters south. All right, if I want to get the average velocity of the ant, okay, average velocity is total displacement divided by total time. Whoop. Okay, so that's what we've got. All right, do I have distance for both parts? Or displacement, sorry, for both parts? I don't, but can I find it? Okay, so I've got to calculate displacement here in part one, which just involves me manipulating B equals D over T for D. So I'm going to multiply both sides by T, okay, and I'm going to have T times V. So 32.5 seconds times 0.25 meters per second. All right, gives me 8.125 meters north. Okay, now I can get the total displacement. Would you agree? Okay, I've got 8.125 meters north and 1.75 meters south. What do I do with those two numbers?
Make the south one negative.
Right, make the south one negative. Okay, remember I was telling you we draw vector diagrams, okay, in a certain way. We draw them tail to head. So this would be my 8.125 meters north. Okay, and then I would have my 1.75 meters south. Okay, that means that this is my total displacement. It is how much I've changed my position by from where I started. And I can get that number by adding negative 1.75 to 8.125, or just subtracting them, which is probably what most of you did. Okay, so if I take my 8.125 and I subtract 1.75, that tells me that the space between those two purple lines is 6.375 meters north. Okay, I still need the total time. I haven't got the time in part two, but I can find it. Okay, if V equals D over T, and I want to get T by itself, I multiply both sides by T, and then I divide both sides by V. So that's going to be 1.75 divided by 0.135, okay, to get our time for part two. All right, so that part takes 12.96 seconds, which then I can put here. All right, and then I just have to put those into the calculator, and I will have my average velocity. All right, so 6.375, my total displacement, divided by my total time. Okay, it's 0.49, because we only have 2 significant digits, I believe. Yeah, we only have 2 significant digits, so 0.49 meters per second. Which way? North.
And wouldn't you add that 12.96 to the 32.5?
Oh, sorry, did I not do that?
No.
Okay, it's much slower than that. Okay, good catch, good catch. You are absolutely right, I should do that. And I should own my awful mistake for not doing that. Okay, sorry, 12.96 plus 32.5. Total time is 45.46, much bigger. Okay, now we'll do the correct calculation. Okay, so 6.375 divided by the now correct time. All right, 0.14 meters per second. North. Is everybody happy with that answer? You should be. Yeah. All right, questions on that?
Would it be 0.140 meters?
Nope, because this number here only has 2 significant digits. Leading zeros are not significant. Okay? All right, before we go back up, we still got some time here. Next week, we are going to start on graphing. Okay, we're going to have position versus time and velocity versus time graph review on Monday. Pretty sure I have the lab for Tuesday. Okay, now you also will have a quiz on Tuesday. Okay, and I'll post that on Monday after school, a practice quiz, okay, for you to do. Okay, but that's what's coming up. We definitely have our first lab Tuesday or Wednesday of next week. Okay, and then yeah, review of position versus time and velocity versus time graphs, which we should be able to get through pretty quickly because we're not changing anything from what you did in Science 10 with those 2 concepts. Okay, so just as if I have this position versus time graph, so meters here, time in seconds here. Okay, what's the object doing right there? Assuming that's perfectly horizontal.
No.
Not moving. Okay, I know that this object is not moving because it means its position is not changing. It is staying at this same position that entire time. What's the object doing here?
Going backwards.
Going backwards at a constant velocity as well. Okay, we know that because the line is straight. Okay, the position changes by the same amount every second during that interval. Okay, so then once again, this means the object is not moving. Okay, its position isn't changing. Okay, here it would be
Moving forward.
moving forwards. Okay, what does that mean? It's accelerating. Okay, it's going faster and faster. Okay, and here's why. In equal time intervals, the object goes further each time. This line gets longer in an equal time interval. Okay, that means it goes further in the same amount of time. The only way to do that is to be going faster and faster and faster. Okay, that's the kind of stuff that we will review next week. Seems like you guys have a pretty good grasp of that already. Okay, all right, good job today, guys.